Okay, we're going on to part 3 of chapter 7 of conceptual physics. It's the work energy theorem. Let me dismiss my image here and continue. The work energy theorem is any change in kinetic energy is the result of work. In equation form, the work equals the change in kinetic energy. So W equals delta KE, where KE is the kinetic energy. After starting from rest, an object obtains twice the speed if subject to the four times of 4 times the work. So if you increase the force by 4 times, you're going to double the velocity. If you increase the distance by 4, you're going to increase the velocity by 2. Let's see. Okay, it applies to decreasing speed also. Reducing the speed of an object or bringing it to halt will also cause that's a change in kinetic energy, because V final is 0 minus V initial. You come up with a number. That's a change. That's a delta. So that's a change in the kinetic energy. So that requires work. Applying the brakes to slow a moving car. The work done on the car is the friction force supplied by the brakes times the stopping distance. Okay, let's see. A fast-moving crate slides across a factory floor subject to a known frictional force. The crate slows down and eventually stops. Which of the following equations most directly determines the stopping distance? Well, that's easy to see. All we have to do is look and see if we have a distance in any of these formulas, and which of those has a distance in it. Well, it's D. Force times distance equals 1/2 mv squared. And there it is, D. The work energy theorem is the physicist's favorite starting point for solving many motion-related problems. Okay. The work done in bringing a moving car to a stop is the force of tire friction times the stopping distance. So the initial speed of the car is doubled. The stopping distance is reduced, about the same, doubled, or none of the above. Well, in this case, it's none of the above. Doubling the speed quadruples the kinetic energy and therefore requires 4 times the stopping distance. So they didn't give you that option here in this question. So it's none of the above because it's 4 times. Okay. The law of conservation of energy. Energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy in the universe never changes. So energy transforms without net loss or net gain in the operation of a pile driver. So if you raise this pile driver up, as you drop it, that potential energy turns into the kinetic energy, which drives this stake further into the ground. Now here's a little example of conversion of kinetic energy to potential energy. At the top of this image, the diver has 10,000 joules of potential energy and 0 kinetic energy because he's standing, he's not moving. Now you can see how his potential energy, as he goes towards his little bucket, decreases. What happens to his kinetic energy? It increases. Here it's potential is 7,500. Here it's the kinetic energy is 2,500. Here, at the midpoint, it's half and half. 5,000 joules of potential energy, 5,000 joules of kinetic energy. Here, as he keeps going, he keeps getting faster. So his potential energy is only a quarter of what it was, 2,500, but it's 3/4 of what it was. His kinetic energy, a 3/4 increase. I said that wrong. It's an increase by 3/4 here. And at the bottom, he's reached full kinetic energy and no more potential energy because his distance is 0. He's reached the bottom. I'm going to do a new share, and I'm going to go to our old friend, Walter Fent, And we're going to see this exchange. Let me do a reset. And I've got, you can look at the elongation, the velocity, the acceleration, the force, or the energy. And we're going to choose energy. And I'm going to put it in slow motion. Now, at the top here, you can see that the potential energy is maximized. So it's going to, it's maximum here. It's going to, as it goes through the zero crossing, it's going to have maximum kinetic energy, zero potential energy. As it goes beyond the halfway point, it's going to slow down because it's stretching the spring, and it's going to go from kinetic energy to, and it's going to come to a stop. You know, at the end of this spring, it's going to come to a stop. So the velocity is zero. So the kinetic energy is zero, and it's going to become all spring potential energy. It doesn't say gravitational and spring potential energy, but those are the two. At the top, it's gravitational. At the bottom, is spring potential energy. Now let's start it. And as we watch this thing, as it moves, well, that's a little slower than I want, but that's okay. There, it's all kinetic energy as you go through the quiescent point. Now you can see the potential, and it's slowing down, and the kinetic energy is building up. That's spring kinetic energy, and it's just a constant exchange as this thing goes up and down of potential energy and kinetic energy. It's always kinetic energy at this zero crossing because that's when it's going its fastest. It's going, it's going to slow down here. There, it's all potential energy. Let's speed it up. Let's play in fast motion. You can see at the two endpoints at its high peak and its low peak is where it's all potential energy. And at the zero crossing, at the quiescent point is where it's all kinetic energy. Okay, that's a good little demonstration. Let's go back to the PowerPoint. Okay. Conservation of energy, a situation to ponder. Consider the system of a bow and an arrow. In drawing the bow, you do work on the system and give it potential energy. When the bowstring is released, most of the potential energy is transferred to the arrow as kinetic energy and some as heat to the bow. We often things are heated up. I mean, if there was no transfer of heat to energy, a pendulum would continue to, whether it be a spring pendulum like we saw in the Walter Fendt example, or just a swinging pendulum, because of as it swings, you're warming up the cable that's suspending the pendulum, and you're warming up the air molecules that are around it as they provide wind resistance. All of those things would, if there were no those resistances, and if you weren't warming up the different parts, it would run forever. But it doesn't, because it's converting some of the energy into heat. Okay. Suppose the potential energy of a drawn bow is 50 joules, and the kinetic energy of the shot arrow is 40 joules. Then energy is not conserved. 10 joules go to warming the bow, 10 joules go to warming the target, or 10 joules are mysteriously missing. Well, they're not missing. They don't disappear. It goes into warming the bow, and the answer is B here. The total energy of the drawn bow, which includes the poised arrow, is 50 joules. The arrow gets 40 joules, and the remaining 10 joules warms the bow. Okay, the similarities between momentum and kinetic energy, both are properties of moving things. If you have no velocity, you have no momentum, and you have no kinetic energy. So they're both have to have a velocity in order for there to be momentum or kinetic energy. The difference between momentum and kinetic energy is the momentum is a vector quantity and therefore is directional and can be canceled. Kinetic energy is a scalar quantity and can never be canceled. It's always, you can have, when we looked at some of the momentum problems. You could have negative velocities, and that canceled out, like in a cannon or in a rifle. You have the total momentum is zero. If it's zero before firing the cannon or the rifle, it has to be zero afterwards. So you have mv in one direction and mv in the opposite direction, and they cancel. That is not the case with kinetic energy. Okay. Kinetic energy is and momentum are both velocity dependent. Momentum depends linearly on velocity. Kinetic energy depends on the square of the velocity. Remember, it's 1/2 mv squared. An object moving with twice the velocity of another with the same mass has twice the momentum, but 4 times the kinetic energy. Okay, and that's the end of part 3, the work energy theorem. And we'll finish up this chapter in the next video.